A sky just 2.7 Kelvin lets stars build order. Here is the cheat code: order survives by dumping heat away. Space is a freezer, and hot things can breathe there. Think of a furnace venting outdoors, not into your room. That vent is the difference between pattern and mush. We will follow that difference across scales, from atoms to webs. Order in physics means constrained arrangements that resist random mixing. Chaos means many similar arrangements where details stop mattering. The second law says overall randomness grows, not vanishes, yet local pockets can sharpen while excess heat spills outward. Bottom line, the universe sorts chaos by exporting it elsewhere. Steam fogs the window while an ice cube slumps into water. Entropy, simply, counts how many micro-arrangements look macroscopically the same. You care because it decides which story's nature keeps running. Heat flows from hot to cold, and possibilities multiply. Molecules spread, collisions scramble details, and unlikely alignments dissolve fast. Patterns fade unless they hitch a ride on flowing energy. A shuffled deck has more similar arrangements than a tidy stack. Energy spreads because more arrangements share that spread evenly. Cold absorbs fine details, while hot sources forget their past. In crystals, atoms repeat in neat rows across long distances. In liquids, positions constantly rearrange, trading order for mobility. That is why melting explodes the count of possible states. Example in real terms: melt a 100-gram ice cube. The entropy jump is about 120 joules per Kelvin. That tiny number multiplies everywhere, across every clinking glass. One sentence recap: entropy grows when energy spreads into more configurations. So order fights back only by steering where energy goes. Sunlight hits a blue marble and darkness above swallows glow. Free energy means energy you can actually turn into work. It matters because without work, structure stalls and memory erases. You need two places, a hot source and a cold sink. The source gives energy, the sink accepts waste, and order persists. Carnot showed the ceiling for perfect engines between two temperatures. The sun sits near 58.0 Kelvin, while Earth sits near 300 Kelvin. The theoretical ceiling is roughly 95% efficient. Reality sits lower, but the principle drives everything alive. Earth absorbs about 120,000 terawatts from incoming sunlight. It returns similar power as infrared into a frigid sky. Plants capture a sliver, then dump heat while building tissues. Animals chain that sliver into motion, then pay the bill. Computers take electricity, warm their chips, and emit infrared glows. Cities shine at night because waste light and heat leave. Rule of thumb: complexity thrives when gradients stay wide and steady. Net result: hot minus cold equals room for order to grow. A silent cloud hangs in space, then starts to crumple inward. Gravity looks like a sculptor of order, yet boosts entropy overall. That contrast matters because galaxies form while the second law survives. As gas falls, potential energy converts into heat and light. Radiation flees into space, carrying disorder away from the clumping core. The core sharpens, while the universe takes the mess as glow. Often, about half the energy heats gas, half leaves as light. Magnetic fields and turbulence open channels to shed additional energy. Without cooling lines from atoms, collapse would stall under pressure. Molecules like carbon monoxide radiate at specific frequencies during collapse. A sun-sized star binds with about 2 × 10⁻41 joules. Much escapes as light during formation and later through fusion ash. So the star gets crisp because the cosmos absorbs the clutter. Tiny test: does structure appear without a place to dump heat? Answer: no, collapse stalls unless radiation vents the rising thermal pressure. Bottom line: gravity organizes locally by exporting chaos through starlight. Boiling oil breaks smoothness and honeycomb cells flicker into place. A dissipative structure is order maintained by a constant flow. You should care because hurricanes, flames, and biology follow this rule. A gradient pushes, nonlinearity amplifies, and a pattern locks in. The pattern survives only while energy moves through and out. When the fuel stops, the order decays and turbulence returns. Convection cells appear with squares, then choose a single rolling direction. In a shallow pan, Baynard cells arrive once heating crosses a threshold. They draw heat upward in rolls a few centimeters wide. Storms feed on warm oceans, then exhaust aloft into cold air. Biochemical cycles move electrons downhill, storing fractions briefly in molecules. Cells export entropy through membranes that act like tiny radiators. Jupiter's Great Red Spot feeds on shear and has persisted centuries. Its organized swirls live by bleeding energy into surrounding winds. One sentence recap: flow creates islands of order within a river. So complexity is not a frozen crystal, but a living process. Across billions of light years, matter threads into luminous filaments. The cosmic web is the universe's scaffolding for galaxies and gas. It matters because those threads decide where stars can grow. Tiny early ripples, 1 in 100,000, seeded the large map. Dark matter collapsed first, pulling normal gas into crowded intersections. Shocks heated the gas, while some cooled and rained inward. Halos merge along filaments, growing cities where highways cross. Cooling times, shock heating, and metal enrichment set the tempo. New stars exploded, stirring turbulence and pushing fresh gas back out. Black holes lit up, launching jets that throttled runaway starbirth. Surveys map filaments using millions of galaxies as bright points. Simulations match those maps when feedback knobs stay balanced. Example: in real terms, filaments span hundreds of millions of light years, yet only a few % of gas becomes long-lived stars. Rule of thumb: feedback keeps galaxies from hoarding fuel too fast. So the web stays dynamic, neither frozen nor fully chaotic. A tiny demon Imagenes sorting fast and slow molecules for free. Information in physics is a physical thing with energetic cost. That matters because cheating entropy would require cheating memory, too. When you measure, you store bits, which must be erased later. Erasing a bit costs at least kT log 2 energy. At room temperature, that is roughly 3 times 10 to the minus 21 joules. Laboratories have measured this limit with tiny nanoscale memory devices. Results align with the prediction within careful experimental errors. Information lets you predict, then shave uncertainty into structure. But bookkeeping lives in atoms, not some weightless mathematics. Memory elements flip states, and that friction costs real energy. A billion erased bits still barely warm a grain of sand. Yet the cost is real, and it closes the loophole. Tiny test: can smart bookkeeping beat the second law forever? No, the eraser's heat pays back the stolen order with interest. Net result: separating order needs energy, even when the trick feels clever. An accretion disk blazes, while a black circle swallows the center. A black hole's entropy scales with its surface area, not volume. You care because these objects are chaos champions of the cosmos. Area grows when you feed them, encoding swallowed information at once. Hawking radiation makes them glow faintly, over absurdly long times. Disks form because infalling gas carries angular momentum inwards. Friction and magnetic fields shuffle that momentum back outward. As matter falls, friction heats the disk and photons escape outward. Jets punch through halos, regulating how galaxies feed on their gas. Accretion can convert about 10% of mass into blazing radiation. 1 kilogram yields roughly 10 to the 16 joules of light. A solar mass black hole holds about 10 to the 77 Boltzmann units. A supermassive one can reach around 10 to the 90. Example: in real terms, quasars outshine entire galaxies for millions of years. Bottom line: the brightest engines run by spilling entropy into the dark. Rewind the cosmos and you find a smoother, hotter beginning. The arrow of time is the direction where entropy rises. You should care because memory, aging, and evolution live on that slope. Early space was uniform, meaning low gravitational entropy despite high temperature. Low early clumpiness meant gravitational room to make structure later. Inflation, if right, stretched wrinkles nearly flat before seeds formed. Phase transitions separated forces, creating fresh gradients to exploit. As expansion cooled the background to 2.7 Kelvin, sinks multiplied everywhere. Stars could run hot, while deep space drank their waste heat. The sun glows near 580 Kelvin, Earth radiates near 300 Kelvin. Between them sits a Carnot ceiling near 95%. Real systems use less, yet the breathing room stays enormous. Today, the background cools by expansion, roughly a quarter Kelvin per billion years. That slow cooling keeps the sink open for a long time. Example: in real terms, you eat sunlight degraded by the atmosphere. You radiate warmth to the sky, closing the non-equilibrium loop daily. So the picture is expansion and a low start power enduring order. That cold 2.7 Kelvin sky you met at the start keeps working. It keeps accepting waste heat, while islands of order sketch themselves. Galaxies spin, hurricanes organize, and living cells write temporary instructions. The trick never changes: use a gradient, steer a flow, dump heat. Whenever the vent clogs, order softens and memory washes away. but as long as hot meets cold, patterns will keep rehearsing. You can spot this everywhere once the lens flips in place. Engines, ecosystems, and economies breathe by moving energy downhill. Their beauty lives in the exports, not the hoarded fuel. If that picture clicked, share this with one curious friend. It helps new islands find their energy and stay afloat. Thanks for watching, and keep an eye on the quiet sky.